go. Hello, everybody. Should be the correct ping going out today, I think. Yo. This song's fun to play on guitar. Falling Fire. Forester, eh? I'll have to check it out post-class. Oh, how's everybody holding up in a post-exam world? It's a world after exams. Oh. I thought I was one of the later ones. Well, today I learned. Work 57 has an exam on Friday. Aw, doesn't sound like much fun. Doesn't sound like fun at all. Good. Alright, I suppose that means it's that time of day. How was your post-exam? You know, for as much as I really dislike Blackboard, it was really easy to grade your exams, and that surprised me. Um, Usually exams take me a solid 3 to 4 days per class to grade, and this one I was able to zip through. But that's me. I don't have the stress of having to study and all that. Mine's just the stress of hard labor. Oh, Blackboard is awful. Come on. It is functional, but the interesting thing I've learned is that computer science people have a particular set of needs for a learning management system, and the rest of the world does not have those needs. Like, You all saw the coding questions on the exam and what a butchery that was for your answers. Um, I don't want to show anything on stream, but looking at some of your copy and pasted Visual Studio code, it was like in a column about this big, and I had like, it was awful. And then some of your exams was, or some of yours were like perfect copy and paste, just beautiful formatting and all of that, and it just seemed random, like why it squished some people's and some looked fine. Yeah, yeah, that's true. Um, I'm glad that question wasn't too bad. Doesn't sound like fun at all. Yeah, that sounds pretty rough. I used Blackboard last semester for my graduate class, and it worked great, except it would crash Chrome on me every time I alt-tabbed out of Collaborate, which is delightful when you're the one running this session. Um, okay, so we can get going then. In terms of the exam, so thank you everybody who emailed me your answers and those of you that resubmitted when I asked for a resend on your JavaScript since Outlook blocks anything.js and doesn't let you, download it regardless. I think that worked okay. And they were even called out Blackboard. Nice. Um, yeah, that's good. It's funny. There's actually apparently talks it's in the some of the upper level academic committees to replace Blackboard in the near future. And they're talking about Canvas or Moodle or um, there's one other one they're looking at. I don't remember what it was. It's just going to be another set of headaches. Moodle's not bad. So the funny thing with Moodle, and this is an aside, is I came from a Moodle environment. So at Oakland, it was all Moodle. And it's cool that it's open source, but when your IT department locks everything down and doesn't allow you access to all the benefits of open source, it becomes just another Blackboard. But it's everything's got its own quirks. It's just going to be up to the faculty member to learn those quirks and manage them. Um, so yeah, in terms of the exam, everybody more or less scored pretty much highly, so I don't think I have any massive concerns with your exams unless anybody does. I think there was only one real question where people tended to get it wrong. Um, I will say in some of them I was kind of generous with my interpretation of your responses at times too. Like the pick question, that one is really a graphic specific operation. It's not something that we're typically going to invoke JavaScript for or the browser. But since we're in kind of this weird WebGL browser environment, it's okay, I think. But picking is like if I were to click on something and I do collision detection or I call read pixels to figure out the color or something like that. And in our WebGL, RGL, SL implementation, we don't actually have access to read pixels too. Um, it's not there for us, unfortunately. I'm just kind of scrolling through the exam questions. The only other one was the buffer flip question. I think people struggled with Triangle audiobook coming soon. I did copy them down. I will provide those pretty soon, so I just want to structure them appropriately. They were all delightful. There were some of you that really went with it, which was fun. Um, I think one I probably got a novella about triangles, and it was heartbreaking what happened to that poor protagonist at the end of that story. But to see if I can get a audiobook narrator on Fiverr or something like that. Oh, there are some good ones though. So that question stems from when I was an undergrad, I had a professor who would always give a 5-point bonus question. And his thing was to write a poem or a story or draw a picture making fun of the other faculty. And he'd post them on his office door. So I figured we'd stick to triangles because I'm not sure how well that would play out here yet with some of the other faculty. Anyway, but I think it went pretty well. Um, so what we'll do is Thursday, I'm kind of thinking we'll do a Zoom session with some in-class work. I noticed that it's about that time, and you probably want some hands-on experience with some stuff that we've been working on. So we will do that on Thursday. I'll probably spend some time going through a little bit of it, and then we'll just kind of work through some fun stuff. It's probably going to be more collision detection, 2D based, kind of where I'm thinking it's going to go. This would be a lab that I hadn't planned on giving, but it sounded like it would be fun for you all. Fun in quotes. So that is about where we are at. Um, Other than that, I think we can probably get going. So let's finish up geometry and transforms today. So we have had some time, and obviously we had the exam in between. We started going over our matrices that we're going to be using, right? So we talked about rotation across axes. We talked about, focus please, translations, right? We talked about, started getting into scaling. That's where we're going to pick up today. But basically everything that we are doing now is going to be matrix transforms. Okay, so we're basically just constructing, whoop, that was fun. Almost fell over there. Constructing a 4x4 matrix with a pre-baked formula, and that's going to be how we update things, right? This is what our GPU is really, really good at. So I've got some demos here for you on this one as well, so it's not just going to be all horribly boring. But we talked about these. We have these, basically these are Euler angles, so we'll talk about this a little bit towards the end. Here we're basically breaking our rotational axes into separate matrices. We'll talk about that pretty soon as well. Like if we wanted to rotate about x, this would be our matrix. Rotate about y, this would be our matrix. So this is about where we ended up then, is scaling. Scaling is another matrix to fill in. All right, so here we have our cosines or sines. When we talk about shear, we'll have cotangents. Scaling's easy. We are going to have an identity matrix, and then whatever is going to be on this diagonal here, it's going to be our scale factor. All right, so if you leave these all as 1, nothing changes. If you update these, it will either stretch or skew your object in that particular fashion. All right, so if I made s dot x or sx like 1.5, 1.5, 1.5, I would expect to see my shape grow by 1.5 times. And so we can actually take a quick look at this here too. VS Code, the correct one. Come here, please. All right, so this first example we're going to look at is cube.html. Cube, not Rubik's Cube solution. So that's this guy. I didn't put a set interval in here at all. Actually, let's do that because this is going to drive me up the wall otherwise. So request anim frame, make sure I'm not blocking anything. Okay. Set interval. This should look familiar. Make this 100. So let's lock down this cube. That's still doing it. Oh, there we go. Okay. Getting some interesting behavior there. Sure didn't leave anything commented out. Yeah, it should be fine. Okay. My computer is unhappy at the moment, I think. Oh, let's just call it. Yeah, leave it as that. What is going on here? I've got something spiraling out of... Okay. Just looking at my task manager, I've got some things that are just destroying my CPU and my RAM. So, bizarre behavior. Anyway, neither here nor there. We have a cube that is rotating. So this is chapter 4, cube.html on the GitHub site if you want to play around with it. But what we are going to do is let's do some scaling. So I'm actually going to leave the JavaScript code alone, and we're going to play with our shader a bit. So if we take a look at this shader, what it's doing is it's basically calculating out, well, first it's taking the theta value that we pass in, and this is pretty much the same that we've been doing before, right, where we have a theta and we pass it along to our shaders to have, things rotate based on this angle. So here's your theta loc equals get uniform location program theta. So this is the same thing that we did in 2D, except now let's convert it to radians. We're going to get a vec3 based off of this. And then let's calculate a vec3 based on the cosine and the sine of those 3D angles, basically. And this particular setup is going to do a couple things for us. First, we only have to do one sine and one cosine calculation here for a rotation, and then we can fill in our matrices appropriately. So these should look pretty familiar here. Let me, not sure why formatting is so wonky. Let's align these just for my anal retentiveness. No tab. Okay. So ignore this SC right here. This is for in a few minutes. But here we are calculating our angles for each rotational axis. Right, so here you have our cosine x value, or sine x value, negative sine, cosine. Basically, we're just filling in each rotational matrix based on what you saw in the slides. And I think there might be some typos with the negatives, so go by what is in the GitHub repo, because I think I have a negative off in places. But there's our Rx, Ry, Rz. And what we see here, we're multiplying Rz times Ry times Rx times V position. And this is giving us our rotation there. So all we're doing is multiplying matrices here. Rotation, though, we already talked about rotation. Let's turn this into a scale factor now. So I'm going to comment this out. I'm going to uncomment this one. Here I've got a scale matrix. So along this diagonal, 0.5, 0.5, 0.5. And I'm going to leave the rotations in. Okay, so I'm not going to comment that out. Refresh. It's a little bit smaller now. How cool. And I'm not sure I'm getting this awful behavior here. Should not be. It's starting to irk me. If we get rid of the request anim frame. Maybe that was it. Nope. Just my computer being my computer. Shouldn't be jerking like that. No, not settings. Elderly professor yells at task manager. Having 30 different instances of Google Slides open doesn't help either. Anyway, what have we done here that is important? We have applied the scale matrix. We are multiplying it with our rotational matrices. Okay. Now, what if I take out the rotational matrices? What do we think is going to happen? Nothing, right? It's not rotating. Nothing's updating. No rotation. Put our matrices back in. Rotation. What if I made this 1.5? It's going to be skewed in the y direction because this would be our y parameter. If I made it in the z direction, can't really see it, but we have an actual interesting behavior kind of happening here. We have some clipping action going on. So it's basically kind of violating our clipping plane in this case. Shake your fist. Yes, absolutely. Angry man yells at clouds. Yeah, clipping planes are fun to play with. One other thing we can do too here, let's move this. So let's put SC right there. Yeah, it's doing some interesting things. I did not update this guy. So one thing that we also are noticing here, so basically what I did was I put the matrix back to where it was before, so we're scaling everything by a half. I took that matrix and I moved it from here to here. Okay, so I changed its location in the order of things. What's kind of interesting is that these operations tend to be commutative, which means they're the same forwards as they're backwards. It's kind of another nice benefit that we have, and we'll get into that a little bit more pretty soon to kind of demonstrate what's going on there. But um, scaling, rotating, all we're doing is multiplying things together. And one other thing that we can do, which I'm not going to get into probably until next time would be my guess, is that we can actually save these transformations as well. Like we don't have to recalculate it every time if it makes sense. We can basically push it down into an array and pull it back up later as we need. One other thing we can do, what if we want to reflect things? Say that we have our original object and we want to reflect it around x or reflect it around y, reflect it around x and y. Well, just use a negative scale. All right, so let's do this. So I'm going to, let's put this back to where we were. So I'm going to take out the rotation for now. So GL position equals SC times V position. So fixed face here, right? Now this might not actually do anything, so I'm going to leave my mouse right here, so this is the top left corner. If I change this to, say, negative 0.5, save. This isn't going to do anything fun. I made them all negative. Yeah, okay, there we go. We're going to look at the different face, basically. Let's change these all to 1. So we have an identity matrix. We're just flipping everything around. There's our blue face. Let's make this one positive. There's our red face. But basically what we can kind of get at with this is that we are playing around with rotation. This would look a little bit more exciting if I didn't have a square object set up here. I don't really want to take the time to go through doing it to, say, a triangle on stream, wasting your time for that. But if we put our rotation back in, it should look pretty similar. Because we're rotating a square, nothing's or a cube, nothing's going to happen for us there. But reflection, just do a negative scale. Kind of the key takeaway. Come back. Thank you. Oops. Now, one other thing that we can do, oh, you know what? I think I've got a slide out of order here. Yeah, sorry, I'm missing something. I must have either accidentally moved it or something of that nature. Slides go out of order, my brain completely shuts down. This is fun. All right, so let's play around with our inverses then a little bit. Or it's not. We'll save this for later. Because one of the things that we're going to be talking about are inverses, so I think I just dragged the slide into the wrong spot. One of the things that we have to talk about with these matrices that we're doing, and you kind of saw that I did a scale and a rotation at the same time, but these are really just kind of matrices being multiplied by each other, right? what we are going to do is effectively form an order of transformations here. So if we want to do a particular thing to a model or to a polygon or whatever we're going to be doing, we may need to actually construct our matrices in a particular way. So we might want to say translate it first, then rotate it, then translate it back. As the spoiler, that's going to be how we rotate something somewhere in space. But to get to that point, we kind of have to understand how matrix math works when we are multiplying things together. If we have, say, a set of transforms that we want to do, doesn't matter what they are, at least in this 4x4 space, they're effectively multiplied rightmost first. Okay, so if we go back to our code here, when we're multiplying things, we see scale, rotate, 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 points. All right, so this could be S, R, 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 P, if we're using our symbols that we have here. Basically what's happening is that the rightmost matrix is going to be applied first when we go through our multiplications. All right, so just kind of keep that in mind if you're trying to concatenate things together, that the rightmost will be done first. And there's, kind of a good reason why this is the case. So let's say that we have the need to scale, move, and then rotate. If we wanted to do that, if we wanted to actually construct a transformation matrix based on this operation, scaling by 80% goes to the right, then translate goes to the left of it, and then rotate goes to the left of that. If you're reading this intuitively, it doesn't make sense. If you're just reading this as code, you think rotate and then translate and then scale, but it's actually the rightmost first. All right. So let's say that we've done this, okay? So take your cube, scale it, move it, and then rotate it. What happens if we do this in reverse order? So let's say we have done our, let me grab Kirby here because he's a nice squishy guy. All right, so we have our Kirby, we scale him, we move him, and then we rotate him. What happens if we reverse the order now? So we rotate, translate, and then scale. Kind of a loaded question. What if we reverse the order, basically? Take Kirby down while I recaffeinate. All right, Kirby's here. Wouldn't it do the same thing? Well, it would, but technically what would happen is we would go back to, sorry, I want to rotate, translate, and then scale. Yep. We go back to something called an identity matrix. So this is basically going to be our initial state, right? An identity matrix has a very particular meaning for us. So let's, I guess let's keep that in mind. Yeah, a little bit convoluted, but we'll clear things up with some demos too. So one of the things that we did with our cube demo was that we broke it down into angles. All right, so if we go back to our cube.html here, we see this Rx, Ry, Rz matrices that are constructed. Again, these are cube.html, the basic one. These are basically rotating around a specific axis. So we're going to call these Euler angles, and they don't commute. So what that means is that based on the order that we are multiplying them, you can't reverse things. This is one of the nifty things about rotational matrices. So I mentioned that we could move the scale around, but we have to leave the rotation angles in the particular order. Otherwise, things don't work out too well. All right, so just basically I'm trying to give you some rules that we have here. So we have that one. But now let's say, okay, we know how to rotate, we know how to scale, know how to translate, we even know how to concatenate them. What if we want to rotate around somewhere else? So we have Kirby here. Kirby is at the origin, okay? My phone is the origin, x-axis. I want him up here, so he's already translated. Okay, so we have instantiated him. He's moved over here. This is my origin. How do we rotate him up here? Because the interesting thing, he said, being somebody in his mid-30s dangling a Kirby doll at a screen, questioning his life's choices. um, if I rotate him up here, he's going to go around this axis, right? We want him to rotate about his origin. But if we're like this, he's going to rotate around the actual WebGL origin. Any guesses on what we have to do? The hint is we have to do more than one thing. I guess let me know if I've lost you as well. I know I had some slide issues, so hopefully that didn't break things up too much. But we have to move the origin. Kind of, yeah. So we have to move him. Translate to origin, rotate, translate back. Absolutely. So it's like somebody might either understand this already or has the slides open. But if I'm up here and I want him to rotate correctly, move him to the origin, do the rotation, then move him back. So exactly right, Skits and Mittens. Best, great name from, is that a It's Always Sunny reference, or? But yep, what we have to do here is that our rotation matrices are going to be calculated based on our world origin. So we have to ensure that we move our object to the world. So all that means is that let's do, no thanks, not today, Google. Translate, rotate, translate back. Okay, so I'm going to start flinging some definitions at you here as well. And again, translate is just going to be moving with that D or negative D, just kind of depends on where you want it to move to. We have that 4x4 matrix that we can just define. One thing we can also talk about is instancing as well. So we may have objects that we are going to instantiate. You know, they could be models, they could be polygons, whatever they're going to be. We can consider them to be an instance when we bring them in, and then we just basically create them. If we are going to be doing some kind of a modeling activity, generally we're going to start centered at the origin with some well-known size, right? So here we have a picture of an apple. Let's say we are modeling a three-dimensional apple, or a three-dimensional Kirby, because he's kind of apple-colored. Start him at the origin, then apply our transformations as we go. And we could apply these transforms to as many instances of Kirby as we wanted. Could go the Smash Brothers Melee, or was it Brawl that had that adventure mode for the first time where they had like a million Kirby spawning on the screen? But we can basically save these transformation matrices and apply them to as many instances as we want. Kind of the key here is that we're trying to, with this notion of instancing, and I feel like I'm not explaining it that well, we want to try and minimize the amount of matrix multiplications we have to do. So if we're going to bring in some objects to our scene, let's always instantiate it the same. All right, so bring it to the origin, orient it perfectly along the axis with a particular size. That way, every time we want to do something to it, we know which matrix to apply, and we can even save that in memory. Right? We don't have to necessarily do anything new. But if I start bringing in multiple, say, phones, where, you know, this is a certain size pixel, then I get the XL, and then I get the Pixel 5 or whatever, and they're all different sizes, they're all different orientations. I'm going to have to construct a whole bunch of matrices specific to each object I bring in. That might be fine, but we're just trying to reduce memory with kind of this notion here. One other thing to bring up now. We have scaling, we have rotation, we have translation, three basic transformations. We have one more called shearing. And this is kind of an interesting one because it uses the little less often used cotangent to do things. If you want a visual of what this is doing, is that we're going to take our object and pull our faces in opposite directions. So if I have, I need like a squishy cube or something. If I've got a cube, I'm going to pull this face this way and this one this way. The angles between them are going to change, right? So I'm going to have, it's going to take a cube like this particular face is going to have the same length here, right? Here to here, here to here. But we're now getting this angle between the two faces. This actually becomes very useful when we start talking about using the camera and doing different perspectives of things. But this is one of the other transforms that we could use if we want to, say, change the shape of something. What does that look like? Well, we have an identity matrix and then a cotangent of some angle theta. And if we wanted to shear something, well, we would just apply this matrix. Pretty straightforward. So the whole point of the set of slides so far really was to introduce you to the different transforms we have. Understand that they're basically just plug-and-play matrices that we drop into OpenGL, WebGL, Unity. Doesn't really matter if we're doing things kind of at this level. We have well-known matrices that we can use. All right, so again, that's what the shear matrix looks like. This has all been high level. Let's do it in WebGL/OpenGL. Now, if you're coming from the OpenGL worlds, we had a lot of extra things to deal with. We have different types of matrices. There's the model view, projection, texture, color. And if we want to change things around, we'd have to set our mode to model view, start tweaking things, and then change the mode again to do, say, something else. We don't have to do this in WebGL. We have a little bit of optimization that has been involved, really. So this particular setup, I should mention too, you just saw the quick preview, this was not very efficient. So if we are going to apply transforms, say I want to do a shear or I want to translate or transform of some way, I need to go to matrix mode, generate my transforms, change my mode again, and do whatever I need to do. This was not very good for the GPU pipeline. Basically what was happening was that everything that we did for our matrices was getting limited and bottlenecked in the CPU, meaning that we can't take advantage of, hey, these lovely GPUs that are really good at matrix math. So it's all been deprecated. What this leads to for us as graphics designers is that we're going to have this notion of something called a current transformation matrix. So a CTM, you may have seen it if you've ever searched for graphics related things. And basically all this means is that we're going to have some matrix that we build up over time where we're just going to apply it to whatever is in our shader. All right, so if it is an identity matrix, nothing happens. It's an identity. That's when it's 1, 1, 1, 1 down the diagonal. Everything else is 0. If I multiply any matrix by that, it will be the same. It's the identity. If we apply a translation, our current transformation matrix is now a translation. I apply rotational matrices. It's now a translation that has been rotated. It's still just one matrix that's getting applied to our vertices. All right, so we're basically just working with one current transformation matrix, as we call it, and we're applying it after everything else has been calculated out. Really nice for the GPU. And this is what it looks like. And again, I'm not really introducing anything new for you here. This is all effectively what we've been talking about, just this is what it's called in OpenGL, WebGL land these days. And if you need a flowchart visual, let's say we have our vertices here, call them vertex array P, or vertex matrix P. We have some transform we're applying. Our new P is C times that, where C is our CTM, basically. Just a matrix math, or sorry, just a matrix multiplication transform. Now we have some basic operations here, and this set of bullets that you're seeing is basically just notation. There's nothing too exciting here to really like memorize or kind of consume. If we want to load something in, we just say M is now C or I is now C. So if I wanted to set up an identity matrix, I just create an identity matrix and say this is my CTM. Or I could pre-construct a matrix and this is now my current transformation matrix. It kind of depends what you need to do. If I want to load in a translation, if I want to load in a scale, a rotation, again, we're just kind of setting basic terms here that we can use later on to understand. If we want to post multiply, and you see C times T, C times R, C times S, C times some matrix, we're just post multiplying. Basically, we're just, whatever the matrix on the right is being multiplied by what we have. Okay, so let's actually take a look at this now. This is where these terms kind of come into play. So if I want to rotate about a fixed point, this is my delightfully introduced example before where this is my origin. This is Kirby. He's up here. We want to rotate him out here. What we would do for notational purposes, let's start with an identity matrix. This is my current transformation matrix. It's an identity, 1, 1, 1, 1, basic matrix. We want to move it. So we're going to say translate to the origin, which just takes Kirby, shifts him down here. Okay. Then we want to rotate. Okay, we're going to do our rotation. I can see his feet. Let's move him back. Goes like this. He's clipping off your camera. Moved him too much. This is where that slide was out of order, by the way. So all we're seeing is how we're building up this current transformation matrix with this notation. And what we get here is a formula, C equals T times R times T to the negative 1. But this is backwards. This does not work. Okay, so let me jump back a couple slides here just to clarify something, because we have this inverse here. Right, so we're saying move the fixed point to the, move the fixed point to the origin. This is a translation matrix. Again, we know what that is. What we have to move in X, Y, and Z to get him to the origin. Do our rotation, whatever we construct for that, and then we're going to say the inverse is moving him back. So let me go back to my inverse slide, which is here. Where were we at? Okay. Right. Let me make a note of this because I'm pretty sure this happened like 2 years ago or whenever it was I last ran this class, and I forgot to move it. Just having bad memories of waffling like in the middle of a lecture. Move back to where you need to go, fool. Okay. You saw nothing. What is an inverse? It means we're doing the opposite operation, right? In terms of matrices, if we do a translation, so let's say we're moving some amount in X, some amount in Y, some amount in Z, the inverse of that means we're applying a negative to each of those parameters. And if we're doing the inverse of a rotation, we're basically going to be using whatever identity we need for that particular operation. So cosine of negative theta is cosine theta, sine of negative theta is negative sine of theta. Basically, we just have these kind of trigonometric identities that we would use to handle an inverse. If you're scaling and you're doing the inverse, it's 1 divided by that scale factor. So if we are shrinking something by a half, the inverse is 1 divided by a half for each of the parameters. Make sense? Hopefully. A little hand wavy since I don't have numbers to fill in for you there, but yep, awesome. Awesome possum. So need to move that back because otherwise the lecture goes smoothly and everything looks wonderful. So we have this result. Excuse me. Translate, rotate, translate, inverse. There's a problem here. if you've been paying attention, the problem is that we remember that we multiply from the right side, correct? So what's happening if we construct it, kind of logically, Kirby starts up here, and we do our first operation is going to be that inverse. Then we rotate him, and he's going to come around, and then we move him back, and he's incorrectly rotated, incorrectly moved. Again, the matrix on the right is done first. So this is post-multiplication at its finest. Basically just reverse the order of our operations here. First thing, create an identity matrix. Then next thing that we're loading in is the inverse, then the rotate, then the translate, then we have things constructed in the correct order. And again, if you're doing this from a shader perspective and we're just doing something trivial like this, what you're seeing here for cube.html, this would be doing a lot of things by hand and not using basically all of our matrix functionalities and multiplication operations, and we're actually like loading things in. For this one, it's not a problem because we can see very clearly we're doing things from the right inwards. But here, we need to be very careful about that. So what we're doing with this current transformation matrix is that we're taking what we knew back in the OpenGL days, and we're trying to emulate it in the WebGL pipeline. Okay, so I'm not trying to expect any prior knowledge of OpenGL from all of you, but basically we're trying to do the same thing that they did, where you remember like would have been last week Thursday now. No, last week Tuesday. We talked about the different steps of our pipeline. There was the world view, then the model view, world view, projection view, camera view, clipping plane, that kind of thing. Our current transformation matrix is going to apply at the model and the projection level. So we can actually use the CTM to, say, get different perspectives as well. And here's my slide talking about it. Here, we can not only, change things around and rotate things, and I lost my cheat sheet of talking points somehow. Hey, nothing there to talk about. We've been talking about this in terms of transformations, in terms of the object model, right? So rotate, shear, scale, whatever we want to do. We can also use it for camera positioning. So this model view matrix can say, if we want our camera to zoom out, right, so let me abuse my actual real world camera here. I instance Kirby at the origin. I want my camera to zoom out. Just move him back here. And everything else back here. The camera hasn't moved, but my perspective has. We can actually use these matrices to do that. However, and this is going to be kind of a cute little shock, we don't necessarily have to do all this horrible math or even mentally think about it. We do have some functions in our application that we can use to kind of help us along the way here. There's a function called lookat in the mv.js library, and there's similar ones in like Babylon and 3.js, all the other libraries that we'll talk about in 2 lectures. Basically, these will construct our camera perspectives for us. If you don't do it, you have to do some extra matrix math that we don't necessarily need. We can also use them to define our view volume, meaning our clipping volume. So what can we actually see? We can pick a camera lens. So let's say that I wanted to do a fisheye camera. We could do that with our model view matrix, with our current transformation matrix. Basically, we can do a lot of things with these matrices. So this code that you're going to see here is actually application code, so keep that in mind. In the libraries that we have available to us here, we can create an identity matrix. Right, so var m equals mat4. So this var should be an instant key that this is JavaScript code, because we don't use var in our shader area, right? So we have a 4x4 matrix. If we want to rotate something, I don't necessarily have to construct a 4x4 matrix with that cosines and sines and all that, I can just say rotate about some theta. And then based on our axes of rotation, we can fill those in as parameters. And here's my rotational matrix. And then I could just say multiply m by r. M being my identity, r being my rotation matrix. Now we just have a current transformation matrix done in 2 lines of JavaScript. So really, we have other options available for us. Can do the same thing with translation and scaling too. So we have functions to construct these matrices in our libraries. These are not standard JavaScript functions, by the way. So don't try to use these without the libraries. But this is kind of some of that hand-holding that I was telling you about, where these libraries kind of shine for us. All right, so I don't have a, let's see. Thought I had a demo there, but I don't. Now let's say that we wanted to do that fixed point rotation. So let's say that we are at some point, 1, 2, 3. So to the right 1, up 2, back in z by 3. If I wanted to do this math that I've been talking about with move it back to the origin, rotate it, move it back, we could construct a matrix here. So translate and then rotate, multiply them together, generate a temporary matrix, and then multiply that by our translation to go back. And don't forget that the last one is the first one applied, so we basically want to order these appropriately, basically. You might also be looking at this and saying, okay, well, we're basically calling M our current transformation matrix here, right? We haven't actually applied it to our vertices yet. We're just constructing 4x4 matrices. What would you do with this? Well, you could pass it on to your shader, for instance, and then let that thing actually handle some of the multiplication math. Performance gains doing this kind of thing in the application versus the shader kind of depends. If you want to be something very, very performant, you probably want to do this all in the shader. You can get away with doing it in the application for kind of low stakes types of applications where performance is not as key, I suppose. Let me do a quick thing off screen here. Okay, it isn't trackball. All right. Just wanted to make sure that I had this demo for you all. Wasn't going to get to it until later, but there is one application demo that we have called trackball. So this is also in chapter 4. Looks kind of like this. I'm going to click and drag. So I'm just kind of clicking and dragging this thing around an axis. This brings up a whole bunch of other questions, but basically it's picking and it's figuring out the angle based on my original point. This particular application does have the matrices being loaded in here. So I've got trackball.js, and let's see if I've got the HTML open. There we go, all the way over here for some reason. So in this application, I'm jumping ahead a little bit, so if you're lost, don't worry. But this is demonstrating these JavaScript calls. Our vertex shader is just saying r times v position. Okay, so our rotation, we're doing nothing with here other than actually doing the math. Again, our fragment shader is just a pass through, it's not doing anything fun. However, our application is doing a little bit more work for us. And there's a lot of stuff in here for figuring out angles of attack with respect to where my mouse is and all that fun stuff. That's kind of not the purpose of this little diversion. But what I'm looking for is the call to mult. So if we are moving, we are constructing a rotational matrix by using our matrix helper calls here. So I'm constructing this rotation matrix, molt rotation matrix times rotate. Again, rotate is one of our helper functions for calculating out, say, like these Euler angles or something of that nature. And then let's pass that to our shader. So do some low-level setup in our application, pass it to the shader, let the shader do the actual hard math, ship it out. But again, this is in MV, and I clicked the wrong thing. I want opened editors. I don't have it open. Harumph. So I just want to kind of show you this. So mv.js, this is one of our libraries. We see function rotate. We see function molt. Funkyton. So again, these are just helping us with some of the basic matrix math. Looking over this, you don't want to do this manually, right? This looks pretty awful. But kind of the key takeaways that we have these helpers for constructing this current transformation matrix. Again, just keep in mind as you're doing this and playing with it too, the rightmost is applied first. A lot of info. Questions so far? If any. Otherwise, I'll keep going. I'm going to try and get through this all today so we can start getting into fun things like Blender and Unity. All good. Good. Sorry, just seeing some notifications, making sure. Okay. This will be actually cool to work with. That's good. Yeah. Once you get past the hurdle of doing the low-level stuff, it does kind of get cool. I talked about arbitrary matrices before. Basically, if you have some kind of a matrix that you're working with, maybe you don't want to start with the identity, maybe you want it to be pre-configured, we can just define it in the application and ship it off to the shader. Again, we're going to think of them as 4x4 matrices. It's going to eventually get flattened and basically turned into a 1x16 matrix. So we will keep that in mind. Oh, actually, I do have it here. For some reason, I was thinking it was in the next lecture. We can keep track of these transformations too. Again, let's say that we have to apply a particular rotation or scale factor or translation multiple times. We can just pop it onto a JavaScript list. OpenGL, if you're coming from that environment, they use stacks. You would push matrices onto the stack and pop them off when you needed them. We can just abuse the JavaScript array, the list notation, whatever your preference for calling it is. You can push and pop, or use your indexing if you'd rather use that. But if you want to save these, you are more than welcome to. And this is the best GIF I could find for stacking. So let's rotate a cube, and we have kind of seen this already. Okay, so I'm going to kind of walk through this fairly quickly here. Cube.html, again, chapter 4. It's going to start rotating, and then we have a button listener changing its direction. So I've got some information for you here. Again, I told you I'd walk through this kind of quickly. The question is going to be for you, the developer, where do you apply these transforms? We have options for us, right? We can do all of our matrix math in the application. Okay, so everything I've been showing you where we construct the map for in the shader, or we generate a current transformation matrix in the application. We can do either, right? We could pre-compute everything in the application and have it be CPU bound. That is technically fine. We could construct that matrix that I was talking about with the, var, I think it was mat equals, I don't want to say the wrong thing now. Var m equals mat4. This was the call that we were talking about. So we could construct our matrix and then ship it along, which is basically, again, what this trackball is doing here. Construct the matrix, send it along to the shader. The question is going to be, what do you do? Now, it can be kind of unclear what your choice is here, honestly. Oops. Depending on how many vertices you have, depending on how much math you have to do, there could be a clear winner that, do it on the GPU. But maybe for ease of programming use, it actually makes more sense to do it in the application. And if you don't have any performance hits, it can really be up to you. You start getting into millions of vertices, then you want to eke out as much performance as you can. But keep in mind that these trigonometric functions that we're working with, right? We're doing cosines and sines and all that fun stuff. These are hard-coded on your GPUs. So there is not any hard math that has to be done if you ship it to the GPU. But it can be a little bit more complicated to understand programmatically. Just kind of keep that in mind. Again, they're all technically fine. It just depends on your use case. All right, so now let's dig into this cube application. I'm going to mainly stick with the slides for this because I've kind of shown you the code already. I have glossed over a few things because I wanted to really highlight some of the various aspects of it. But cube. If we remember in our cube, we have a few buttons here. So let me do the minimize thing. Cube. And I'm using the local copy because I've been dinking around with it. Right, it started out like this. We can change its direction with these on-click listeners. What's happening here is that we are actually updating which theta we are sending based on an index. So we have this current variable axis. So if we look in our JavaScript code here, we see var axis equals 0, var theta equals an array. So here we have our x angle, y angle, z angle. And I'm going to guess that you can make the leap that based on whichever axis we are currently selecting, that will be which index in the list that we ship out. Okay? So if we dig into the code here, we'll get to color cube pretty soon. Everything looks the same. Initialization's the same, shaders are the same. Sorry, shaders are the same. Boilerplate initialization of the buffers is the same. Thanks to all of you in the exam, by the way, who said they felt bad about just copying and pasting all this code because it seemed like plagiarism. This is all boilerplate stuff, so don't worry about that. But colors, vertices, 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 colors. Theta, link up our uniform. Here's our event listeners for picking the axis. And all this is doing is just updating the index for whichever theta is updating every loop. All right, skipping color cube, skipping quad. Every render call, we're basically just going to update whatever theta is currently selected. So that's how we get this singular axis update. I could do something like this. So let me get rid of this guy here. Theta 0 plus equals 2.0. There's probably a nicer way of doing this in JavaScript, but be lazy. So I'm just updating every single axis. What are we expecting to happen? Every single theta will update every single frame. And we get kind of a nifty loopy thing going on here. Hopefully makes sense so far. We're basically just shipping off whatever theta we want based on what is selected. There is one other interesting thing in here, though. We are now in 3D land, right? This is all triangles that we have going on. All right, I need you to stop moving. Please stop. Let's bring you back. Leave you commented out. Okay, we have a static cube. What do we remember from past lectures in the extra credit? This is two triangles, right? So probably triangle 1, triangle 2. How are we representing this in our application? So let me get it rotating this way. We basically have just a bunch of triangles that we're drawing here, right? Everything's a triangle. To help out, and we're going to get into easier ways to do this in the next set of slides, we can define our triangles in kind of interesting ways. So the way that cube.html, cube.js does it here is that we're going to define every single vertex that we need. And we see 1, 2, 3, 4, 5, 6, 7, 8. And then we have the associated colors here that we want to set. These are the vertices that we need to work with. We don't need any more than that. But we are going to need a set of quads. What's a quad? It's a square. Well, it's basically a rectangle. Could have differently sized quads. All this quad function is doing is it's pushing down the vertices that we need for every single square. Okay, so for every square we need 6 vertices, right? Or sorry, 6 vertices. And based on what we know of creating squares, right, if I give it, I guess depending on this, if it's a rectangle, we're gonna have to do a little bit of math, right? But if I have, say, like the top left corner and the bottom right corner, I can figure out what the bottom left and the top right are. So we don't have to go in depth with this particular example or the spelling errors from the book author, but I can just push down 2 triangles, push the associated colors, and then I have a quad. And I can very easily say, okay, which index goes with this particular square. And based on, this is kind of helpful, like drawing out the cube if you want, because you could say this is vertex 0, this is 1, this is 2, this is 3. And then you can very easily build up a shape. So hopefully that makes sense more or less. One other thing we can do here too if you want, because this is kind of fun, because there is a for solid colored faces, use this, where we're basically setting every single vertex to be the same color on the quad. If we get rid of that, and we push down all the vertex colors, we're going to get something pretty like this. Ooh. And again, here we are just basically setting separate colors instead of the same color for each face. And you actually kind of see it clipping off a little bit there. But just a brief aside on coloring. Basically, the point of this little diversion is if you're building up shapes, have some helper functions, right? So don't specify every single vertex one after the other. Here we only define 8, and then we just pick and choose what we need from that. So just a little bit of a helper hint there. That is the application code. Now our shader code. We have these Euler angles that I talked about, and I'm going to kind of zip through this just because I've beaten this to death already. One thing to keep in mind when you are working with these matrices in WebGL, they're column major order, meaning that if you want to index into the array and you want to say like matrix A, bracket 2, bracket 1, that's down 2 over 1, instead of your more common row major where like this would be 1, 2, if that makes sense. Basically in column major order, you just kind of have to look at these subscripts to hopefully help it make sense. This is just how we index into the array. This would be, if I want this particular value here, this would be Rx bracket 0 bracket 1 to get to this point. That makes sense, hopefully. Assuming we're 0 base, this is obviously 1 base here. That's a rotational matrix. Again, you've seen this all. This particular approach, Rx, Ry, Rz, this is actually using Euler angles, so we're not going to talk too much about this. But that's one way of calculating out rotational matrices. So basically you figure out what the particular 4x4 matrix is for every single axis. So again, we see Rx, Ry, Rz. We fill in cosine and sine values as appropriate. So for the x matrix, you see cosine x parameter, sine x parameter, cosine. For the y, it is cosine y, negative sine y. So we see the y parameters in here. For the z matrix, we see the z parameters. These are called Euler angles. It is one way that you can do rotation. If you've ever taken, oh, probably a physics class or a mechanical engineering class, you may have heard of them. If not, no worries. They're not too bad, but they can be inefficient. And if they're inefficient, that's because we have three matrices to construct and multiply here. It turns out that if we go into the imaginary domain, it becomes a lot more efficient. And this is something called quaternions. And if you have or have not heard of these, this sounds kind of far-fetched. If you're a mathematician, you get really excited about them. But basically what we're doing here is that instead of directly figuring out angles, we're going to elevate them to use imaginary numbers. And what this means is that instead of doing things very, very procedurally, very honestly and efficiently, we're going to move to the imaginary domain. We're going to calculate out a quaternion, and then we're going to apply it back to our model matrix. Excuse me. And what this does is that we have a singular real component and a set of imaginary components. Right? And I've got a lovely picture here to help you with this. And this looks horribly complicated. I've got a link to explain this figure after this slide. It's basically a delightful Reddit post in math for visualizing them. But if you take a look at this figure and you actually understand it, it becomes really easy. So on the X, Y, and Z axes here, these are your standard axes, right? So look at kind of the straight lines. So this one would be your Y, for instance. This one could be your Z. This one could be your X. If I want to rotate about one of these axes, so let's pick the Z-axis here. So this is blue. Match up the colors. And if you're colorblind, hopefully the shades of gray match up for you here. But if I want to rotate about this axis here, we'd multiply it by K. So this is in quaternion land. And you can kind of see, so let me get my phone here. So let's say that this is my Z angle here. If I want to rotate this way, we're going to multiply it by K. And to kind of understand that, just look at the colors. So we want to go this way, basically. And that's probably not a great explanation. We've got 5 minutes left, and this is a 10-minute video, 12-minute video. Seriously recommend watching this video because it is awesome for explaining them. Basically, it's getting into fixing a point, going up a level, and then just basically doing some simpler math. It sounds complicated. It's really not all that bad. The problem is it looks horribly complicated in terms of the application. I guess if I recall, the explanation from the YouTube video is that you fix like a point. So if I have an object, I fix it around an axis, and then based on which imaginary number I multiply it by, it will rotate around that axis. So I think he actually uses them to stab something as an example. But I do have a demo here which will show you the code. Hopefully it won't turn you off from it, but it's really not all that bad. Where's it at? Cube, Q. All right, so it is actually this guy. So cube, Q. So I'm kind of zipping through things to get to the end of class. So this is cube Q. So this is multiplying by quaternions. Really, terrible browser performance aside right now, same thing, nothing too crazy. But if we look at the code for it, cube Q, cube Q, where's the other cube Q? you. Where are you? That HTML. Okay. We have a shader that looks like this. So a little bit more complicated, but the math actually works out to be easier, which is an interesting way to talk about it. So basically, here we have our main function. We still calculated our sine and cosine. We're going to generate quaternions. We're going to do some extra multiplications here involving dot products, cross products. If you remember when we talked like day 1 or day 2, we talked about swizzling and selection. Those terms come into play here, where we're selecting the y, z, and w parameters of a matrix. Again, the math actually works out to be a little bit easier for your computer to deal with, oddly enough. Looks hella complicated, but if we can break through the initial difficulty, it's really not all that bad. The JavaScript for it actually looks pretty similar. It's trying to get down to render. We don't actually really do anything different other than package up which theta we're sending, which honestly we did before. It's trying to make sure there was no difference so I don't lead you astray. Yeah. Slightly more complicated math. Again, this kind of a model helps. Just saying multiply it by j, multiply it by k, doesn't really make any sense. Mathematically, this makes sense. We're talking about the actual quaternion construct. Programmatically, we're getting into like dot products and cross products and things like that. But yeah, I would say honestly, homework for the day, watch this video. It is great for explaining it. He also goes into some of the history on it too. So we'll leave it at that. Next time we'll get into building up models. So kind of getting towards this kind of a thing. Any questions for today? Basically just kind of blasting you with definitions and transformation matrices. But if we are all good otherwise, again, we'll probably do a lab on Thursday. I'll send out an announcement for that as well. I'll need to review another. Yeah, quaternions are hard to explain, honestly. Well, they're probably not hard if you're a mathematician, but translating it from the imaginary realm to actual hard programming code is not as easy. And I'm unfortunately intentionally glossing over it. Go watch the video. Yes. Honestly, I probably watch it every time I need to remember how a quaternion works, because it's not something that I have to do day to day. But yeah, next time we will do probably a little bit of model work, a little bit of in-class work, and should be fun. Anyway, and right on time, I will see you all on Thursday. Have a wonderful 60-degree day. Bye, everybody. Let's end with some chill music. Enough chill.